Welcome to the Timeless Science. This is a long-form science documentary focused on deep scientific explanation. Every time a computer deletes a single bit of data, the universe heats up. Not because the machine is inefficient, but because reality demands payment. In this chapter, you will learn why information is not abstract, why forgetting has an energy cost, and how a single principle from 1961 permanently changed physics. You will see how computation became a thermodynamic process, why erasing data increases entropy, and how this insight resolved one of the most famous paradoxes in science. This is the moment when information stopped being mathematics and became part of physical law. In the middle of the 20th century, physics faced a quiet contradiction. On one side stood thermodynamics, insisting that every physical process has an energy cost. On the other stood information theory, treating bits as abstract symbols, zeros and ones that could be copied, erased, and rearranged without consequence. The contradiction was simple and unsettling. If information is abstract, why does every real computer heat up when it works? The answer began with a statement that sounded almost heretical at the time: information is physical. Not metaphorically. Literally. In 1961, Rolf Landauer formulated what would later be called Landauer's principle. It was not a theory about computers in the everyday sense. It was a claim about nature itself. Any logically irreversible operation, most importantly, the erasure of information, must dissipate a minimum amount of energy as heat. Forgetting, in physical terms, has a price. This idea reversed the usual intuition. Engineers had long assumed that computation consumed energy because real machines were inefficient. Friction, resistance, imperfect components. Landauer argued the opposite. Even a perfect machine, built from ideal parts, would still have to pay an energetic cost when it destroys information. The limit is not technological. It is fundamental. To understand why, consider what it means to store a bit. A bit is not an abstract symbol floating in space. It must be embodied in a physical system. A voltage level in a transistor. The orientation of a magnetic domain. The position of a particle in a potential well. In every case, two distinguishable physical states represent 0 and 1. As long as those states remain distinguishable, the information is preserved. The moment they are deliberately made indistinguishable, reset to a standard value, merged, or overwritten, the system loses information. And that loss must show up somewhere else. In a universe governed by thermodynamics, it shows up as heat. Landauer quantified this cost. The minimum energy required to erase one bit of information is proportional to temperature. More precisely, it scales with thermal energy multiplied by the natural logarithm of 2. The exact formula matters less here than its meaning. Information destruction is inseparable from entropy increase. There is no free deletion. At first, this seemed like a philosophical curiosity. Early computers were so inefficient that Landauer's limit was drowned out by engineering noise. But the principle carried a deeper implication. If information erasure has an irreducible energy cost, then information itself must be counted among the physical quantities of the universe, alongside mass, energy, and entropy. This reframed computation as a thermodynamic process. When a computer performs a calculation, most logical operations can be done reversibly in principle. Bits can be shuffled, copied, and transformed without losing information. But real computation eventually requires decisions. Branches collapse. Temporary data is cleared. Memory is reset. Every reset is an act of erasure. Every erasure pushes entropy outward into the environment. In this view, a computer is not just a symbol manipulator. It is an entropy pump. The deeper insight comes from asking why erasure, specifically, is so costly. The reason lies in the distinction between logical and physical irreversibility. A logically irreversible operation maps multiple possible input states to a single output state. Once that happens, the original information cannot be reconstructed from the result alone. Physically, that loss must be compensated by an increase in entropy elsewhere. Otherwise, the second law of thermodynamics would be violated. Landauer's principle therefore acts as a bridge. On one side is Shannon information, the mathematical measure of uncertainty. On the other is thermodynamic entropy, the physical measure of disorder. Landor showed that they are not merely analogous. They are quantitatively linked. This connection had an unexpected consequence. It rescued thermodynamics from a famous thought experiment that had troubled physicists for nearly a century: Maxwell's demon. The demon was imagined as a tiny being that could observe individual molecules in a gas and selectively allow fast ones to pass through a door while blocking slow ones. Over time, it would create a temperature difference without doing work, seemingly violating the second law. The resolution of this paradox had long been debated. Landor's principle provided the missing piece. The demon's measurements could, in principle, be done without cost. But the demon's memory could not grow indefinitely. Eventually, it would have to erase information. And when it did, it would pay the thermodynamic price. The universe allows observation. It does not allow free forgetting. This realization elevated information from a bookkeeping tool to a physical resource. It also imposed hard limits on what any computing system, biological or artificial, can ultimately achieve. No matter how advanced technology becomes, it cannot evade Landor's bound. It can only approach it. Decades later, experiments confirmed the principle directly. Researchers built microscopic systems where single bits were erased under carefully controlled conditions. As the systems were cooled and engineered closer to reversibility, the measured energy dissipation approached Landor's predicted minimum. The limit was not hypothetical. It was real. At that moment, the status of information in physics changed permanently. If information has an energy cost, then it participates in the same accounting rules as everything else. This raises a natural question. If information is physical, where does it reside? Is it stored in particles, fields, or something more abstract? The emerging answer is that information is not tied to a particular substance. It is tied to state. Any physical system capable of existing in distinguishable configurations can store information. What matters is not what the system is made of, but how many distinct states it can reliably maintain against noise. This perspective dissolves the boundary between computation and physics. A crystal stores information in its lattice structure. A black hole stores information in its horizon area. A brain stores information in patterns of neural activity. In every case, information is inseparable from the physical degrees of freedom that encode it. Landor's contribution was not merely a formula. It was a shift in ontology. Information ceased to be a shadow cast by physical systems. It became something that constrains them. From this point forward, questions about information could no longer be delegated to computer science alone. They became questions about the universe itself. How much information can a region of space hold? How fast can information be processed? Can information ever be truly destroyed? These questions will drive the rest of this documentary. But before following them into quantum theory and cosmology, it is worth pausing on the foundational insight. The universe does not care about meaning. It does not care whether a bit represents a number, a word, or a thought. What it enforces, relentlessly, is accounting. If you compress uncertainty, if you discard distinctions, if you erase history, the bill is paid in energy. Information is not free. It never was. That realization marks the true beginning of modern information physics. In the late 19th century, physics encountered a thought experiment that seemed small, playful, almost mischievous. Yet it exposed a fault line running through the foundations of thermodynamics. In 1867, James Clerk Maxwell imagined a tiny being, later called a demon, capable of observing individual molecules in a gas. The demon sits between two chambers separated by a door. As fast molecules approach from one side, it opens the door to let them through. When slow molecules arrive, it keeps the door shut. Over time, one chamber grows hotter than the other. A temperature difference appears. No work is done. Entropy seems to decrease. At first glance, the implication is devastating. The second law of thermodynamics states that entropy in an isolated system cannot spontaneously decrease. Yet Maxwell's demon appears to violate it using nothing more than information and timing. The demon does not push molecules. It does not add energy. It merely knows. For decades, this paradox unsettled physicists. Many suspected a hidden cost, but no one could agree on where it lay. Was measurement itself expensive? Did observation require energy? Or was the demon simply impossible? Early responses focused on mechanics. Perhaps opening and closing the door would require work. Perhaps friction or inertia would restore the second law. But these arguments collapsed under refinement. In principle, the door could be made arbitrarily light and frictionless. Measurement, too, could be idealized. The demon could observe without disturbance. The paradox persisted because it pointed to a deeper confusion: the relationship between information and entropy. Entropy had been defined as a measure of disorder, then later formalized as a measure of the number of microscopic configurations compatible with a macroscopic state. Information theory, developed much later, defined information as a reduction in uncertainty. The two quantities looked similar. But similarity is not identity. For a long time, physics treated them as conceptually separate. Maxwell's demon forced the issue. The demon's power came entirely from information. By knowing which molecules were fast and which were slow, it could sort them. If information were truly free, then entropy reduction would be free as well. The second law would be a statistical guideline, not a fundamental constraint. The resolution required a precise accounting of what the demon actually does. The key insight arrived with the recognition that the demon is not just an observer. It is a memory-bearing system. To function, it must record information about each molecule: position, velocity, timing. Each observation leaves a trace. Over time, that memory fills. At that point, the demon faces a problem. Memory is finite. To continue operating, it must clear space. It must erase information. This is where the paradox turns. Measurement alone does not necessarily cost energy. In principle, a measurement can be performed reversibly, without increasing entropy. But erasure cannot. When the demon resets its memory, when it deletes old records to make room for new ones, it performs a logically irreversible operation. Multiple prior memory states are mapped to a single blank state. Information is destroyed. And destroyed information must be paid for. This is the moment where Landauer's principle enters the story, not as an abstract rule, but as the missing link. Erasing one bit of information produces a minimum amount of heat. That heat flows into the environment. Entropy increases. The second law is restored. The demon does not break thermodynamics. It obeys it more carefully than we first assumed. The crucial point is subtle but decisive. Entropy reduction in the gas is exactly compensated by entropy increase in the demon's memory erasure. When the full system is considered, gas, demon, and environment, the total entropy never decreases. The apparent violation arises only when information processing is ignored. This reframes the second law. It is no longer merely a statement about energy and matter. It is a statement about information handling in physical systems. From this perspective, the demon becomes a prototype of every computing device ever built. Like the demon, a computer gains power from information. It sorts, predicts, and controls. But like the demon, it must periodically erase. Caches are cleared. Registers are reset. Memory is freed. Each act of forgetting carries an entropy cost. The universe does not prohibit intelligence. It prohibits cost-free intelligence. This insight resolves another long-standing confusion. Entropy is often described as disorder, a metaphor that invites misunderstanding. In the demon scenario, the sorted gas appears more ordered. But order is not the fundamental quantity. What matters is the total accounting of distinguishable states across all components. When the demon's memory is included, the balance is restored. The demon teaches us that entropy is not defeated by cleverness. It is enforced by bookkeeping. There is a deeper lesson here. The cost does not depend on what the information means. The demon does not care about the semantic content of its memory. It only matters that distinguishable physical states are being compressed into fewer states. Meaning is irrelevant. Physics counts states, not interpretations. This universality is why the resolution applies across scales. Whether the memory is a notebook, a silicon register, or a molecular configuration, erasure carries the same fundamental cost. The substrate changes. The accounting does not. Maxwell's demon also clarifies why thermodynamic limits are so robust. They do not rely on imperfections or ignorance. They survive even in idealized scenarios with perfect control. The second law is not a statement about human limitations. It is a constraint embedded in the structure of physical law. Once this is understood, the demon transforms from a threat into a guide. It shows precisely where intuition fails and where rigorous accounting must begin. The cost of forgetting is not an engineering inconvenience. It is a feature of reality. This has implications far beyond thought experiments. In modern computing, engineers work constantly to reduce energy dissipation. As devices shrink and efficiency improves, Landauer's limit moves from irrelevance toward inevitability. At small scales, erasure costs dominate. Heat management becomes information management. The demon anticipated this future. It forced physics to confront the fact that information is not merely processed by physical systems. It is a physical process. The second law survives because the universe keeps track of everything that is forgotten. And that principle extends outward. Any system that sorts, predicts, or controls, cells, brains, machines, must obey the same rule. They may locally reduce entropy by creating structure. But they must export entropy elsewhere by erasing information. This is not a loophole. It is the price of order. With Maxwell's demon disarmed, a new question emerges. If information processing is constrained by thermodynamics, what are the ultimate limits of systems that process information continuously and at scale? To answer that, we must turn inward, from idealized demons to the most sophisticated information processors known. Biological ones. Every thought has a temperature. Not metaphorically. Physically. The human brain is often described as an information processor, but this description is usually taken as an analogy. Neurons are said to compute, synapses to store data, spikes to transmit signals. What thermodynamics forces us to confront is that this language is not poetic. It is literal. The brain processes information using physical systems, and therefore it must obey the same energetic limits as any other computer. The question is not whether thinking consumes energy. That is obvious. The question is why it must, and whether there is a fundamental lower bound on the cost of thought. Landauer's principle provides the starting point. Any logically irreversible operation, any operation that destroys information, requires a minimum energy cost. This applies to silicon circuits, molecular machines, and biological tissue alike. If neurons erase information, they must dissipate heat. If they compress uncertainty, entropy must increase somewhere else. To see how this applies to the brain, we must strip away metaphor and look at mechanism. A neuron is not a symbolic processor. It is a physical system that switches between states. At rest, it maintains an electrical potential across its membrane. When it fires, that potential collapses and then must be restored. This cycle is not free. Ions move. Gradients are disrupted. Molecular pumps must work to reset the system. Each action potential is a physical reset. From a computational perspective, a neuron integrates incoming signals and produces an output spike if a threshold is crossed. From a thermodynamic perspective, that spike represents a loss of detailed information about the precise inputs that produced it. Many different microscopic input configurations can lead to the same macroscopic outcome, firing or not firing. That convergence is logical irreversibility. The neuron forgets. And forgetting has a cost. Measurements of neural energetics reveal a striking fact. The brain operates far above Landauer's theoretical minimum. The energy cost per bit processed by a neuron exceeds the fundamental limit by many orders of magnitude. This is not inefficiency in the engineering sense. It is the price of reliability, speed, and noise resistance in a warm, wet biological environment. Thermal noise is relentless. At body temperature, Random molecular motion constantly threatens to blur distinctions between states. To maintain reliable computation, neurons must use energy margins large enough to overpower noise. This requires metabolic expenditure. The brain burns energy not to compute abstractly, but to keep information physically distinguishable. This exposes a critical trade-off. At the Landauer limit, computation is maximally energy efficient but exquisitely fragile. Any fluctuation can corrupt a bit. Biological systems cannot afford this fragility. A single misfiring neuron can have catastrophic consequences. Evolution therefore selected robustness over theoretical efficiency. The result is a brain that is energy-intensive but reliable. Yet even with this margin, the thermodynamic logic remains intact. Every time a neuron resets its membrane potential, it exports entropy to its surroundings. Heat is dissipated into blood and tissue. The skull becomes a heat sink for cognition. Thinking warms you up because it must. This reframes cognition as a thermodynamic process. The brain is not simply consuming energy to stay alive while thinking happens as a side effect. The act of information processing itself is inseparable from energy dissipation. There is no clean separation between metabolism and computation. They are the same process viewed at different scales. This insight generalizes beyond biology. Artificial neural networks, despite their name, are vastly simpler than real brains. Yet they obey the same accounting rules. Training a network involves repeated erasure and updating of internal states. Gradients are computed. Weights are overwritten. Each overwrite is an irreversible operation. In physical hardware, this produces heat. As computational systems scale, the cost of erasure becomes dominant. Modern processors are no longer limited primarily by how fast they can switch, but by how efficiently they can remove heat. The bottleneck is thermodynamic, not logical. This convergence is not accidental. It reflects a deeper constraint. Any system that continuously processes information must pay an entropy tax proportional to the amount of information it discards. There is no workaround. One might ask whether reversible computation offers an escape. In principle, computations can be arranged so that no information is erased. Every step can be inverted. Entropy production can be made arbitrarily small. This is not science fiction. Reversible logic gates exist. The mathematics is sound. But reversible computation shifts the burden rather than eliminating it. To be useful, a computing system must eventually produce an output in a standard, readable form. It must clear temporary storage. It must reset. The entropy bill is deferred, not forgiven. Moreover, reversible systems are extremely sensitive to noise. Maintaining reversibility requires exquisite control over physical states, which itself demands energy. In practice, the thermodynamic savings are consumed by stabilization costs. The brain does not even attempt reversibility. It embraces irreversibility as a design feature. Synaptic changes overwrite old states. Neurons spike and reset. Memories decay. This is not a flaw. It is how biological systems remain adaptable in a fluctuating environment. Forgetting is not a failure of cognition. It is a thermodynamic necessity. This leads to a crucial reframing of intelligence. Intelligence is not the ability to accumulate infinite information. It is the ability to selectively discard information while preserving what matters. The cost of that selectivity is paid in energy. Every act of abstraction, every time a system compresses detailed input into a simpler representation, it destroys information. That destruction is precisely what makes generalization possible. And it is precisely what generates entropy. Seen this way, entropy production is not an unfortunate byproduct of intelligence. It is its enabling condition. The brain's efficiency, measured per useful decision rather than per bit, is extraordinary. Despite operating far above Landauer's limit, it outperforms artificial systems in adaptability, resilience, and contextual inference. This suggests that optimal computation is not about minimizing energy per operation. It is about balancing energy expenditure against reliability and relevance. Thermodynamics does not tell systems how to think. It tells them what thinking costs. This cost imposes hard limits. There is a maximum rate at which information can be processed for a given power budget. There is a maximum density of reliable memory at a given temperature. There is a maximum speed at which decisions can be made without overheating. These are not engineering inconveniences. They are physical boundaries. Once this is understood, the idea of disembodied intelligence collapses. There is no such thing as computation without a substrate. There is no cognition without dissipation. Any thinking system, anywhere in the universe, must export entropy to function. This has implications that reach far beyond brains and machines. If information processing is constrained by thermodynamics at every scale, then the universe itself, if it processes information, must obey the same rules. It must have limits. It must generate entropy. It must pay for forgetting. Before we can extend this reasoning to the fabric of reality, however, one more boundary must be confronted. In classical systems, information can be copied freely. Bits can be duplicated. Redundancy can overcome noise. At the smallest scales, nature refuses this convenience. To understand why, we must turn to quantum information, and to a rule that forbids perfect copying outright. Classical information is forgiving. A bit can be copied, then copied again. Redundancy can be added at will. Noise can be defeated by repetition. If a classical system becomes unreliable, the solution is simple: make more copies. At the quantum scale, this strategy fails completely. In 1982, physicists proved a result that at first sounded like a technical limitation, but quickly revealed itself as a fundamental rule of nature. The no-cloning theorem states that it is impossible to create a perfect copy of an unknown quantum state. Not difficult. Not impractical. Impossible. This was not an engineering constraint. It was a theorem derived directly from the structure of quantum mechanics itself. The result was independently formulated by William Wootes and Wojciech Zurek, and it reshaped how physicists understood information at the most basic level. To see why the theorem is so profound, we must be precise about what it forbids. In quantum mechanics, the state of a system is described by a wave function. This wave function encodes all measurable information about the system. Unlike a classical bit, which is either 0 or 1, a quantum state can exist in a superposition of possibilities. It is not merely unknown before measurement. It is genuinely undetermined. Cloning such a state would mean taking an arbitrary, unknown wave function and producing an exact second copy, without disturbing the original. Classical intuition suggests this should be possible. After all, if information is physical, why should physics forbid duplication? The answer lies in linearity. Quantum evolution is linear. Any physical process that copies a state would have to work for all possible states. But when the mathematics is written down, a contradiction appears. A machine that perfectly clones one quantum state necessarily fails for another. There is no universal copying operation compatible with quantum laws. Nature does not merely discourage copying. It forbids it. This single result has sweeping consequences. It explains why quantum measurement is irreversible. It explains why quantum information cannot be treated like classical data. And it explains why uncertainty in quantum mechanics is not a limitation of knowledge, but a structural feature of reality. From an information theoretic perspective, the no-cloning theorem introduces a radical asymmetry. Classical information can be backed up arbitrarily. Quantum information cannot. There is no redundancy strategy that preserves a pure quantum state without alteration. Information at the quantum level is fragile by design. This fragility is not accidental. It is inseparable from the same principles that give quantum systems their power. Superposition and interference allow quantum systems to encode correlations that have no classical counterpart. Those correlations cannot be duplicated because doing so would require extracting information that does not exist in a classical sense prior to measurement. Attempting to copy a quantum state forces a choice. Either information is extracted, collapsing the state, or the state is preserved but no copy is made. There is no third option. This stands in stark contrast to classical thermodynamics. In classical systems, irreversibility arises primarily from coarse graining and ignorance. At the quantum level, irreversibility is built in. Certain transformations are forbidden even in principle. The no-cloning theorem therefore marks a boundary. It tells us that information, once encoded in quantum degrees of freedom, is subject to rules stricter than those governing energy or matter alone. This boundary has a direct thermodynamic interpretation. In classical computation, redundancy can reduce error at the cost of additional energy. In quantum computation, redundancy cannot preserve unknown states. Error correction must take a different form. It relies not on copying states, but on distributing information across entangled systems in carefully structured ways. This is not a loophole. It is a consequence. Quantum error correction works precisely because it avoids cloning. Information is not stored in individual components, but in correlations among them. Lose one piece, and the information may survive. Attempt to duplicate the whole, and the structure collapses. Here, information is no longer local. This changes the thermodynamic landscape. In classical systems, erasure costs arise from compressing distinguishable states. In quantum systems, distinguishability itself is constrained. Certain states cannot be distinguished without being destroyed. Measurement and erasure blur into a single act. As a result, quantum information processing intertwines thermodynamics and measurement more tightly than any classical analog. The cost of acquiring information, the cost of losing it, and the impossibility of copying it are all facets of the same constraint. The universe is not merely charging for forgetting. It is restricting what can be remembered in duplicate. This has consequences for causality and communication. Because quantum states cannot be cloned, they cannot be broadcast. This prevents a host of paradoxes. Faster-than-light signaling schemes fail because they rely, implicitly or explicitly, on copying quantum information. The no-cloning theorem enforces causal order without invoking additional postulates. Information security also changes meaning. In classical cryptography, secrecy depends on computational difficulty. In quantum cryptography, secrecy is guaranteed by physical law. Any attempt to intercept quantum information necessarily disturbs it. Eavesdropping leaves a trace because copying is forbidden. This is not technology outperforming theory. It is theory dictating what technology can ever become. At a deeper level, the no-cloning theorem forces a rethinking of identity. In classical physics, identical copies are indistinguishable. In quantum physics, identical preparation does not imply identical state. Two systems prepared in the same way may still be fundamentally uncopyable after the fact. Information acquires history. This matters for thermodynamics because entropy accounting depends on distinguishability. If states cannot be freely duplicated, then entropy cannot be arbitrarily diluted by replication. The classical trick of spreading information across many copies to reduce local cost does not generalize. Quantum mechanics closes that escape route. Seen in this light, the no-cloning theorem is not an isolated curiosity. It is a statement about how the universe limits information flow. It constrains memory, communication, and control at the smallest scales. It ensures that certain kinds of order cannot proliferate unchecked. The rule is simple. You may transform quantum information. You may move it. You may entangle it. But you may not copy it perfectly. Nature enforces scarcity at the level of information itself. This scarcity prepares the ground for the next concept. If quantum information cannot be copied, how can it be shared at all? How can distant systems exhibit correlations stronger than any classical channel allows, without violating causality or thermodynamics? The answer does not lie in transmission in the usual sense. It lies in entanglement. At first encounter, quantum entanglement seems to promise exactly what physics has just forbidden. Two particles interact. They separate. Yet measurements performed on one appear instantly correlated with measurements performed on the other, no matter how far apart they are. The correlation is stronger than any classical explanation allows. Outcomes appear linked across distance without delay. To early readers of quantum theory, this looked like communication faster than light. It is not. Entanglement does not transmit information. It structures information. This distinction is not semantic. It is the difference between a paradox and a physical principle. Entanglement arises when multiple quantum systems are described by a single, inseparable quantum state. The systems do not possess independent properties. Only the combined system does. Individual outcomes are undefined until measurement, but the relationships between outcomes are precisely constrained. The information is not in the parts. It is in the correlations. This is why entanglement survives the no-cloning theorem. No individual quantum state is copied. Instead, information is distributed non-locally across a composite system. Destroy one piece, and the information may still be recoverable. Attempt to duplicate the whole, and the structure collapses. Entanglement is not a channel. It is an architecture. To understand why this matters, consider what communication actually requires. A signal is a controllable change that can be modulated by a sender and decoded by a receiver. Entanglement provides no such control. Measurement outcomes are fundamentally random. No choice made at one location can force a specific outcome at another. This is why entanglement cannot be used for faster-than-light signaling. The correlations only become visible when results are compared using a classical channel, which is limited by the speed of light. Until that comparison occurs, each local observer sees only randomness. Causality remains intact. Yet the correlations themselves are real. They are stronger than any classical correlation allowed by local hidden variable theories. This was made precise by Bell's inequalities, which quantum systems violate and classical systems cannot. The universe permits correlations that cannot be decomposed into independent local properties. This is the key shift. In classical physics, information is local. The state of the whole is the sum of the states of its parts. In quantum physics, this additivity fails. The whole can contain information that does not reside in any part individually. Thermodynamically, this changes how information is stored. In a classical memory, adding redundancy means copying bits. Each copy carries an energy cost. Each reset carries an entropy cost. Reliability is purchased through duplication. Entanglement offers a different strategy. Information can be protected by encoding it into global correlations rather than local states. This is not free. Creating entanglement requires interaction and energy. Maintaining it requires isolation from noise. But once established, entanglement allows information to be robust against certain local disturbances without relying on copying. Quantum error correction exploits this principle. Logical information is encoded across many physical qubits such that no single qubit contains the information by itself. Errors affecting individual components can be detected and corrected without measuring the logical state directly. Again, no cloning occurs. No forbidden duplication takes place. The protection comes from structure, not replication. This reframes the role of entropy. In classical systems, entropy increase often corresponds to loss of correlations. In quantum systems, entropy can increase locally while global correlations persist. A subsystem may appear thermal and random, while the total system remains in a pure, low-entropy state. This is not a loophole in thermodynamics. It is a reminder that entropy is observer-dependent. What counts as disorder depends on which degrees of freedom are accessible. Entanglement hides information from local observers. This hiding has a thermodynamic signature. When a system becomes entangled with its environment, local entropy increases. Information about precise states is delocalized into correlations with degrees of freedom that are no longer accessible. From the local perspective, information is lost. From the global perspective, it is conserved. This is the mechanism behind decoherence. Quantum systems appear classical not because quantum laws fail, but because information leaks into entanglement with the environment. Phase relationships become inaccessible. Superpositions effectively collapse. The environment becomes a vast correlation sink. Importantly, this process does not destroy information in principle. It makes it unrecoverable in practice. Reversing decoherence would require controlling astronomical numbers of correlated degrees of freedom. The thermodynamic cost of such control renders reversal physically impossible, even if not forbidden by equations. Here, thermodynamics and quantum mechanics align. Information is conserved globally, but entropy increases locally because access is limited. Entanglement therefore plays a dual role. It preserves information at the fundamental level while enforcing irreversibility at the practical level. It allows the universe to be reversible in theory and irreversible in experience. This duality resolves a tension that has haunted physics since the 19th century. Microscopic laws are time reversible. Macroscopic phenomena are not. Entanglement provides the bridge. Time symmetry holds globally. Entropy increase emerges from the spreading of correlations beyond reach. Seen this way, entanglement is not exotic. It is ubiquitous. Every interaction entangles systems. Every collision, every emission, every absorption event creates correlations. The classical world emerges not because entanglement is rare, but because it is everywhere. Information is constantly being pushed into correlations we cannot track. The universe does not lose information casually. It buries it. This has implications for information storage at extreme scales. If correlations carry information, then the capacity of a region to store information depends not just on volume, but on how correlations can be structured across boundaries. This insight leads directly to a surprising conclusion. The maximum information content of a region does not scale with its volume at all. It scales with its surface. This is not intuition. It is a bound. And it brings us to the next step in the journey, the realization that space itself may be constrained by informational limits. To understand those limits, we must ask a sharper question. How much information can any finite region of the universe possibly contain? For most of the history of physics, information was assumed to scale with size. A larger box could store more particles. More particles meant more states. More states meant more information. The intuition was simple. Double the volume, double the capacity. Space was treated like an empty container whose informational potential grew with how much matter it could hold. This intuition turned out to be wrong. In the early 1970s, Jacob Bekenstein proposed a radical idea. There exists a fundamental upper limit on the amount of information that can be stored inside any finite region of space. Not a technological limit. Not a practical constraint. A bound imposed by the laws of physics themselves. This limit is now known as the Bekenstein bound. Its statement is deceptively simple. The maximum information content of a region does not scale with its volume. It scales with the area of its boundary. This was a shock. To understand why, we must follow Bekenstein's reasoning carefully, because it did not begin with information theory. It began with black holes. At the time, black holes were treated as peculiar but straightforward solutions of general relativity. They swallowed matter. They trapped light. And, according to classical theory, they erased all detailed information about what fell inside. This posed a problem. If information were truly destroyed, entropy would decrease. The second law would be violated. Bekenstein proposed a solution. Black holes must carry entropy. And that entropy must be proportional to the area of the event horizon, not the volume inside it. This was already a departure from classical intuition. Entropy had always been associated with volume, the number of microscopic configurations available within a region. Black holes inverted that logic. Their entropy scaled with surface area. From this insight, a deeper consequence followed. If a black hole represents the most efficient possible way to pack entropy into a region of space, then no physical system confined to that region can exceed the entropy of a black hole of the same size. Otherwise, collapsing the system into a black hole would reduce entropy, violating the second law. This argument does not depend on the nature of the system. It does not matter whether the region contains gas, radiation, computers, or living beings. The bound applies universally. Entropy has a ceiling. Translated into information language, the implication is stark. There is a maximum number of bits that can be stored in any finite region of space. That maximum is proportional to the area enclosing the region, not the volume it encloses. Information is not volumetric. It is geometric. This result reshapes the meaning of storage. In classical systems, information density can be increased by packing components more tightly. In quantum gravity, that strategy fails. Beyond a certain point, adding more energy to a region does not increase its information capacity. It turns the region into a black hole. At that point, the boundary becomes the memory. The Bekenstein bound also connects information to gravity in a precise way. The bound depends on fundamental constants: the speed of light, Planck's constant, and the gravitational constant. Information capacity is not a matter of convention. It is woven into space-time itself. This marks a turning point in the story. Up to this point, information appeared as something processed by systems within space. With the Bekenstein bound, space itself becomes part of the information budget. Geometry constrains memory. Gravity enforces limits on knowledge. This has immediate consequences for computation. Consider any hypothetical supercomputer confined to a finite region. No matter how advanced its design, no matter how perfect its components, it cannot store or process information beyond the bound imposed by its enclosing area. There is a maximum memory density. There is a maximum processing rate consistent with that memory. The universe does not merely tax computation energetically. It caps it structurally. This limit is absolute. It does not care about materials or architecture. It does not depend on error correction or clever encoding. It is a consequence of preventing gravitational collapse. Information that tries to exceed the bound collapses into a black hole and becomes encoded on a horizon. The boundary wins. This result also clarifies the relationship between entropy and ignorance. Entropy is not simply a measure of disorder. It is a measure of how many distinct internal configurations are compatible with the same external description. The Bekenstein bound limits that number by limiting how much can be hidden behind a boundary. There is only so much that can be concealed. From a thermodynamic perspective, this introduces a new kind of irreversibility. Once information is compressed beyond the bound, it becomes inaccessible to observers outside the region. Recovery would require accessing the horizon itself, which introduces its own limits. Information is not destroyed. It is sequestered. The bound also resolves a potential conflict between quantum mechanics and gravity. Quantum theory allows arbitrarily large Hilbert spaces. Gravity forbids arbitrarily dense storage. The Bekenstein bound reconciles these tendencies by restricting which quantum states can coexist in a given spacetime region. Not all mathematically possible states are physically realizable. This is a profound constraint. It means that physics is not just about what equations allow. It is about what spacetime can sustain. The consequences ripple outward. If information capacity scales with area, then the degrees of freedom describing a region of space may reside on its boundary rather than in its interior. Volume becomes emergent. Surface becomes fundamental. This idea will later crystallize into something even more radical. But here, at the level of the bound, it already undermines classical assumptions. The universe does not store information the way we store data in a box. It stores information the way a horizon does. Every finite region is subject to this accounting. Every memory, every archive, every record in the universe ultimately competes with gravity. Information is constrained not just by energy and noise, but by spacetime curvature. This places a final, non-negotiable ceiling on accumulation. Intelligence can grow. Knowledge can expand. But storage cannot diverge without limit in a finite world. The Bekenstein bound therefore completes a sequence. Landor showed that erasing information costs energy. Maxwell's demon showed that forgetting pays the entropy bill. Quantum mechanics showed that information cannot be freely copied. And gravity now shows that information cannot be packed arbitrarily densely. Each step tightens the net. Information is physical. Information is costly. Information is scarce. The next question is unavoidable. If information is bounded by horizons, what happens in the most extreme case of all, where the horizon is absolute? To answer that, we must return to black holes themselves, and to a paradox that sits at the heart of modern physics. Black holes were once thought to be simple. According to classical general relativity, a black hole is fully described by just a few parameters: mass, charge, and angular momentum. Everything else about the matter that formed it, the shapes, structures, compositions, and histories, vanishes behind the event horizon. From the outside, the black hole forgets. At first, this seemed acceptable. After all, classical physics had no obligation to preserve detailed information forever. But when quantum mechanics entered the picture, this apparent simplicity became a crisis. Quantum theory is built on a strict rule. The evolution of a closed system is unitary. Information is never destroyed. It may be transformed, scrambled, or rendered inaccessible, but it cannot disappear completely. Probabilities must always add up. Past states must, in principle, remain recoverable from the present. Black holes appeared to violate this rule. The paradox sharpened dramatically in the 1970s, when Stephen Hawking made a discovery that shocked the physics community. Black holes are not perfectly black. Quantum effects near the event horizon cause them to emit radiation. This radiation is now known as Hawking radiation. The consequences were profound. Hawking radiation is thermal. It carries no information about what fell into the black hole. It depends only on the black hole's mass, charge, and spin. As radiation escapes, the black hole loses energy. Over immense timescales, it shrinks. Eventually, it evaporates completely. If the radiation is purely thermal, then when the black hole disappears, the information about everything that ever fell into it is gone as well. This is not merely inconvenient. It is catastrophic. If black holes destroy information, then quantum mechanics fails. The fundamental consistency of physical law breaks down. Predictability collapses. The universe becomes non-unitary. This is the black hole information paradox. At first, Hawking embraced the implication. He argued that black holes genuinely destroy information, and that quantum mechanics must be modified to accommodate this fact. Information loss, in this view, was a real physical process. Many physicists were unconvinced. Among the most vocal critics was Leonard Susskind, who argued that information loss was unacceptable. If black holes destroy information, then the foundations of quantum theory collapse everywhere, not just near horizons. The paradox could not be localized. It infected the entire framework. The debate that followed was not a technical disagreement. It was a clash between two pillars of physics. On one side stood general relativity, with its horizons and causal disconnection. On the other stood quantum mechanics, with its demand for unitarity and information conservation. Both theories were spectacularly successful. Both appeared non-negotiable. Something had to give. The key difficulty lies in how information is distributed during black hole evaporation. From the outside, Hawking radiation looks random. Each emitted particle carries no identifiable imprint of the matter that fell in. Early in the evaporation process, this randomness is expected. But as evaporation continues, a problem arises. If information is preserved, then late-time radiation must somehow be correlated with early-time radiation. Information must be encoded non-locally across the entire emission history. The radiation cannot be independent thermal noise. It must be structured. But classical calculations show no such structure. This creates a tension between semi-classical gravity and quantum information theory. Semi-classical calculations treat spacetime as fixed and quantum fields as small perturbations. In that framework, information is lost. But quantum mechanics insists that this framework must be incomplete. The paradox therefore signals a breakdown of approximation. One possible resolution is that information escapes with the radiation, but in a form so scrambled that it appears thermal locally. The correlations are subtle, spread across many degrees of freedom, and invisible to any observer who measures only a small portion of the radiation. In this view, information is not destroyed. It is delocalized. This idea aligns with earlier insights about entanglement. Hawking radiation is entangled with degrees of freedom behind the horizon. As evaporation proceeds, that entanglement structure must evolve. Eventually, the radiation must become entangled with itself in just the right way to preserve information globally. This requires a dramatic departure from classical intuition. It implies that spacetime locality breaks down at the horizon. Information that appears trapped may not be confined in the way general relativity suggests. Another proposed resolution invokes remnants, stable, Planck-scale objects that survive evaporation and store the information. But remnants introduce severe problems. They would require infinite storage capacity in a finite object, violating the very bounds established earlier. Other approaches modify the nature of horizons themselves. The event horizon may not be a passive boundary. It may encode information dynamically. From the outside, the black hole behaves like a hot, dissipative system whose surface degrees of freedom carry the entropy. In this picture, information is never truly inside the black hole in the classical sense. It is stored on or near the horizon, encoded in microscopic degrees of freedom that semi-classical theory cannot resolve. This idea is radical, but it fits a pattern. Entropy scales with area. Information capacity scales with area. The horizon behaves like a memory. The paradox then becomes a guide rather than a failure. It tells us that space-time geometry alone is not sufficient to describe reality at extreme conditions. Information must be built into the fabric of gravity itself. Over time, the balance of opinion shifted. Most physicists now believe that information is preserved in black hole evaporation, even if the exact mechanism remains under active investigation. Hawking himself eventually conceded the point. The paradox did not disappear. It matured. It forced physics to accept that locality, as defined by classical spacetime, cannot be fundamental. At horizons, information behaves in ways that defy naive geometric separation. What falls in and what escapes out are not independent stories. Black holes do not forget. They scramble. This scrambling is extreme. Information is mixed so thoroughly that reconstructing it would require access to the entire radiation field and control over correlations at a staggering level of precision. In practice, recovery is impossible. In principle, it remains allowed. Thermodynamics is satisfied. Quantum mechanics survives. But only by abandoning the idea that spacetime is the final stage on which physics plays out. The black hole information paradox therefore marks a turning point. It shows that information is more fundamental than geometry. It constrains gravity, not the other way around. To resolve the paradox fully, physics must adopt a new organizing principle, one in which information, not spacetime volume, defines the degrees of freedom of a region. That principle is already waiting. It begins with a simple but shocking claim. The universe may be holographic. The idea begins as a constraint, not a speculation. If the maximum information content of a region scales with its surface area, then the familiar picture of space as a volume filled with independent degrees of freedom cannot be fundamental. Something deeper must be organizing reality. The interior cannot contain more information than the boundary allows. This realization led to one of the most radical proposals in modern physics, the holographic principle. In the early 1990s, Gerard T. Hooft argued that all the information describing a volume of space could be encoded on its boundary, with no loss of physical content. The idea was later developed and sharpened within string theory, but its origin was thermodynamic and informational, not speculative. The principle states that the degrees of freedom of a region of space are equivalent to degrees of freedom living on a lower dimensional surface that encloses it. 3 dimensions reduce to 2. Volume gives way to area. Depth becomes redundant. The analogy to optical holograms is intentional. A 2-dimensional holographic plate encodes all the information needed to reconstruct a 3-dimensional image. Every part of the plate contains information about the whole image, though with varying resolution. Likewise, in a holographic universe, the boundary encodes the interior. This is not an analogy about appearance. It is a claim about physical bookkeeping. The motivation comes directly from black hole thermodynamics. Black hole entropy scales with horizon area. The Bekenstein bound limits information storage by area. The information paradox demands that information not be destroyed. The holographic principle unifies these facts into a single framework. If information is stored on boundaries, then black holes no longer pose a paradox. The horizon is not hiding information inside a volume. It is the volume's information. This reframing dissolves the contradiction. But the principle goes further. It suggests that spacetime itself may be emergent. The geometry we experience could arise from patterns of entanglement and information encoded on lower dimensional structures. In this view, space is not fundamental. Information is. This is not philosophical excess. It is forced by consistency. Consider entropy again. Entropy counts distinguishable states. If the number of distinguishable states inside a region is bounded by the area of its boundary, then any theory that assigns independent degrees of freedom to every point in the volume is overcounting. The true degrees of freedom must be fewer and differently organized. Holography provides that organization. The most concrete realization of the principle comes from a correspondence between two seemingly unrelated theories. A gravitational theory defined in a higher dimensional spacetime can be mathematically equivalent to a non-gravitational quantum theory defined on its lower dimensional boundary. Every physical process in the bulk has a precise description on the boundary. Nothing is lost. Nothing is added. The descriptions are equivalent. This equivalence is exact, not approximate. It implies that gravity itself can emerge from information dynamics in a system with fewer dimensions. Spacetime curvature corresponds to entanglement structure. Distance corresponds to correlation strength. Geometry becomes a secondary concept. Thermodynamics again provides the logic. If entropy is fundamental, then geometry must accommodate it. The holographic principle enforces entropy bounds by construction. It prevents information overload by never allowing volume to exceed its boundary's capacity. This changes how locality is understood. In a holographic description, what appears local in the bulk may correspond to highly non-local patterns on the boundary. Conversely, simple local interactions on the boundary can generate extended structures in the bulk. Locality becomes emergent, not primitive. This is why holography resolves the black hole information paradox. Information does not cross the horizon in the classical sense. It is encoded in boundary degrees of freedom that remain accessible in principle. Hawking radiation can carry information because the boundary already contains it. Scrambling replaces destruction. The principle also explains why gravity is weak compared to other forces. If gravity is an emergent effect arising from collective information dynamics, its apparent weakness reflects the coarse-grained nature of the description. The fundamental interactions occur at the level of information, not spacetime force carriers. From this perspective, spacetime is a bookkeeping device. This does not mean the universe is a projection in the everyday sense. Objects do not flicker in and out of existence. Causality is not violated. Physical laws remain consistent. What changes is the hierarchy of concepts. Information comes first. Geometry follows. The holographic principle also imposes limits on simulation. A region of space cannot be simulated with arbitrary fidelity by a system smaller than its boundary area allows. There is no shortcut. The universe enforces matching information budgets. This reinforces a recurring theme. Information is scarce. Information is structured. Information is constrained by physical law. The principle does not claim that we live on a literal surface. It claims that the fundamental description of reality may require fewer dimensions than we perceive. The extra dimension is an emergent construct, useful but not primary. This is why holography is not optional. It is demanded by the combination of quantum mechanics, thermodynamics, and gravity. Without it, information accounting fails. With it, paradoxes dissolve. Yet holography raises a final, unsettling question. If space emerges from information, then what is information itself made of? If boundaries encode everything, what determines the rules by which that encoding occurs? To answer that, physics must take its last step in this journey. It must ask whether the universe, at its deepest level, is not merely constrained by information, but built from it. The final step in this journey is not a conclusion. It is a synthesis. After thermodynamics imposed a cost on information, after quantum mechanics restricted its copying, after gravity capped its density, and after holography relocated it to boundaries, one question remains unavoidable. Is information merely constrained by physical law, or is physical law itself a consequence of information? This question defines the digital physics hypothesis. At its core lies a simple but unsettling claim. The universe may be describable as a self-consistent information processing system. Not a computer in the everyday sense. Not a simulation running on external hardware. But a closed system whose fundamental degrees of freedom are informational rather than geometric or material. The most influential articulation of this idea came from John Archibald Wheeler, who summarized it in a phrase that has echoed through modern physics: it from bit. The phrase is often misunderstood. Wheeler was not claiming that the universe is literally made of zeros and ones. He was pointing to something more precise. Physical entities, particles, fields, spacetime itself, may emerge from binary choices, from yes or no questions posed by the act of measurement. Reality, in this view, is not a collection of objects. It is a network of answers. This idea did not arise in isolation. It was forced into consideration by the same pressures we have traced throughout this documentary. Information behaves too much like a fundamental quantity to remain secondary. It obeys conservation rules. It incurs costs. It obeys bounds. It structures correlations. It constrains geometry. At some point, the hierarchy must invert. Digital physics proposes that information is primary, and that the laws of physics describe how information can be transformed consistently. This does not mean that everything is discrete in a naive sense. Quantum mechanics already warns against that simplification. Quantum states form continuous spaces, but measurement outcomes are discrete. Information sits at the interface between continuity and discreteness, mediating what can be known and recorded. The hypothesis therefore does not claim that the universe is a cellular automaton or a finite-state machine. Those are models, not commitments. What it claims is more restrained. The ultimate description of physical law may be informational, not mechanical. In this framework, particles are excitations of informational structure. Fields are rules governing correlations. Spacetime is an emergent ordering principle that reflects how information is organized and constrained. Crucially, this is not metaphysics. It is an attempt to unify limits. Consider the recurring pattern. Every time physics encounters an apparent infinity, information theory intervenes. Infinite energy densities are cut off by quantum mechanics. Infinite information densities are cut off by gravity. Infinite copying is cut off by the no-cloning theorem. Infinite reversibility is cut off by thermodynamics. The universe does not allow unlimited description. Digital physics treats these cutoffs not as inconveniences, but as clues. They suggest that physical law is less about dynamics unfolding in a pre-existing arena, and more about maintaining internal consistency in an informational system with finite capacity. This perspective clarifies why many physical constants appear finely tuned. They are not arbitrary knobs. They define thresholds that keep information processing stable. Too much freedom, and predictability collapses. Too little, and complexity never emerges. The universe exists in a narrow informational corridor. Within this corridor, computation occurs everywhere. Not computation as deliberate calculation, but as state transition. Every interaction processes information. Every correlation stores it. Every decoherence event redistributes it. The universe computes itself forward in time by updating its informational state. But here the hypothesis must remain disciplined. Digital physics does not claim that the universe has intentions, goals, or awareness. It does not imply purpose. It does not require an external observer. The informational update rules are internal. Measurement does not require consciousness. It requires interaction. Information, in this context, is not knowledge. It is distinguishability. This distinction matters. Confusing information with meaning leads quickly into philosophy. Digital physics stays on physical ground. It asks what distinctions can exist, how they can be preserved, how they can be transformed, and what constraints govern those transformations. Meaning is optional. Accounting is not. One of the strongest motivations for digital physics comes from quantum gravity. Attempts to quantize spacetime directly have repeatedly run into inconsistencies. Treating geometry as fundamental leads to infinities and ambiguities. Treating information as fundamental allows geometry to emerge as a derived concept. In holographic models, spacetime distance corresponds to entanglement structure. In this context, geometry is not assumed. It is reconstructed from correlations. This is a profound shift. Instead of asking how matter moves through space, Digital physics asks how information organizes itself such that space appears. Time becomes an ordering parameter for informational updates. Causality becomes a constraint on allowed correlations. Nothing supernatural is added. Something familiar is removed. Space-time loses its privileged status. Yet the hypothesis remains cautious. It does not claim to be proven. It does not override established theories. It functions as a framework, a way of aligning thermodynamics, quantum mechanics, and gravity without contradiction. Its strength lies in coherence, not finality. Importantly, digital physics avoids a common trap. It does not claim that reality is a simulation run on a computer elsewhere. That idea adds unnecessary assumptions. It duplicates the problem rather than solving it. Digital physics is internal. The universe is not simulated by something else. It is described by information because information is the only invariant currency across all scales. This returns us to the beginning. Landor showed that information erasure costs energy. Maxwell's demon showed that forgetting enforces entropy. Neural systems showed that thought dissipates heat. Quantum mechanics showed that information cannot be cloned. Entanglement showed that information lives in correlations. Gravity showed that information density is bounded. Black holes showed that geometry must respect information. Holography showed that space itself may be informationally encoded. Digital physics does not add a new principle. It connects the existing ones. The universe does not merely contain information. It is constrained by it. And those constraints may be what we call physical law. This does not answer every question. It reframes them. Instead of asking what reality is made of, physics increasingly asks what distinctions reality can support. What correlations can exist? What transformations preserve consistency? What information can survive? In that sense, the universe is not a machine. It is not a mind. It is not a program. It is a self-consistent informational structure that evolves according to rules that prevent contradiction. That may be the deepest law of all. And it brings us to the end of this journey, not with certainty, but with clarity. Information is not a metaphor. Information is not optional. Information is not free. It is the scaffold on which reality stands. Goodbye. Or perhaps, see you in the next frame of understanding.